This video is going to help us learn how to use the z-interval to calculate a confidence interval for proportion. So there's a lot of words going on in that can be overwhelming. So basically what we want to create is we want to create a range of numbers in which we feel confident that our proportion will fit. And the big thing about this video and about this lesson is it is a process. Now, this video series for this unit has been talking about developing a systematic process to work through the problems. And if we continue to use that approach, we will continue to improve and have a good chance to be successful. So a confidence interval is where we can make a statement of confidence about an unknown proportion. And we're going to see that in a few minutes. So this example number 1 will illustrate the process, and then we'll look at it with some numbers. So example number 1, what proportion of times will a thumbtack land pointed side up? All right. So the process for this is number 1, calculate the p-hat. As we've learned in video lessons before, the p-hat is calculated by the number of times successful over the total sample size. Right. Then again, from a previous video lesson, determine if the sampling distribution of p-hat meets our normal distribution requirements. Rule of thumb number 1, we can assume yes. So rule of thumb number 2 and rule of thumb number 3. Take a minute or two just to confirm that those two requirements do exist. Right. From there, the third step, we can estimate the standard deviation of p-hat using this formula that we investigated in a previous lesson, the square root of p parentheses 1 minus p parentheses all divided by n. This is where we need to make another little connection here, is that as we go through this process, because it is normally distributed, p-hat becomes that p. So the p value that you have in this square root formula is the p-hat value that we calculate in step 1, because it becomes normally distributed. That's what allows us to do that. Right. Step number 4, construct an interval based upon p-hat by adding and subtracting 2 standard deviations. So this interval that we see here, our interval will be p-hat plus or minus 2 standard deviations. So if we can calculate what p-hat is and we can calculate what our standard deviation is, then the interval that we create will be plus or minus 2 of those standard deviations. Right. And then number 5 is how we can make our conclusion statement. This is the inference that we want to draw. Because we checked that we are allowed to use the normal distribution, and because the empirical rule that we learned previously states that 95% of all observations fall within 2 standard deviations of the mean, then we can say this method will capture the true proportion 95% of the time we use it. Right? So that's a fancy little paragraph that boils down to the statement that you see in the middle of the screen. The statement that we want to be able to make is, I am 95% confident that the true proportion is between that interval that we get by doing p-hat minus 2 standard deviations and then p-hat plus 2 standard deviations. So again, this is the system, the step-by-step systematic process that we're going to practice today and hopefully learn how to do. And what I've learned through my years of teaching is students who successfully learn this systematic approach are very successful with this. They don't get overwhelmed by looking at the problem and saying, I don't know what to do. They look at step 1, step 2, step 3. And as they work through one step at a time, they aren't overwhelmed by how complicated the whole problem may look. Right? So now let's actually put some numbers to it. So let's suppose I flipped a thumbtack 50 times. So 50 times is the sample size n, and counted 28 times it landed point up. So those two numbers will help me create the p hat, the proportion of point up. So that p hat will be 28 times successful over 50 times that I flipped a thumbtack. And when I divide that, that gives us a probability of 0.14. Now, number two, determine if that sampling distribution meets our two rules of thumb. Right, so again, the 50 is the n. So rule of thumb number two, does 50 times 0.14, is that really greater than 10? Well, yes, check, it is. Is 50 times 1 minus p. So again, we need to calculate that 1 minus p. So 0.14 is p hat. That p hat becomes our letter p. So that 0.14, because we will eventually see it is normally distributed, that 0.14 is our letter p. So 1 minus p, 1 minus 0.14 equals 0.86. So does 50 times 0.86, is that greater than 10? Check, it is. So both of those two requirements are met. Step number three is where we're going to use that square root formula from a previous lesson. Estimate the standard deviation of p hat. So it's 0.14, parentheses 0.86. Divide that by the sample size of 50. And Desmos is a great tool to help us do that calculation. So the square root of 0.14, parentheses 0.86, close the parentheses, divided by the sample size, 50 times I flipped the thumbtack, and I have a standard deviation of 0.0491, would be a good way to round that off. 0.0491. Everything that I've worked through with steps 1, 2, and 3 are all based off of prior knowledge of things that we've learned. Now, in previous lessons, we would take that information, we would put that into a normal distribution format, and we would analyze that so we could answer questions about various other things. Today, we're not going to do that. Instead, we want to construct a 95% confidence interval. So again, 95% confidence using the empirical rule, that is 2 standard deviations. So to create that 95% confidence interval, we'll start with 0.14 and then add or subtract 2 times that standard deviation of 0.0491. If we start with 0.4 and subtract 2 standard deviations, then start with 0.4 and add 2 standard deviations, our 95% confidence interval will give us the numbers 0.0418 and then 0.2382. So the conclusion statement that we can make, I am 95% confident that the true proportion of thumbtacks landing point up is between these two numbers that we've just calculated, between 0.0418 and 0.2382. So using what we've learned in previous lessons, we know that with that sample size of 50, if I flip it 50 times again, I'm going to get different than 28 times it lands heads up. So I know that 28 is not a true proportion for every time we do it. But this 95% confidence interval says that I am 95% confident that for every time I flip it 50 times, I will get a true proportion somewhere in that range of 0.0418 to 0.2382. That's what this 95% confidence interval is about. Now, a part of the objective that we had mentioned something called the Z interval. All right, so let's see what the Z interval is about. So confidence interval, one proportion Z interval. Well, to factor in a margin of error, we can use this confidence interval table to calculate what level of confidence we want to use. So the empirical rule for our normal distribution says that 2 standard deviations 95% of all data should fit within 2 standard deviations. Now, to account for and factor in a potential margin of error, if you look at the confidence interval table, 95% we can actually use the decimal 1.96 instead of the full 2. That just allows a little bit of a margin of error. So this Z interval that was referred to in the objective gives us, instead of using exactly 2 times that standard deviation each time, we can use this factor that goes with each percent. So if we want to say 80% confidence, then we would use 1.282, 85%, 90%, and so forth. The one that is used most common is that 95% confidence interval. Now, we will practice some problems where it may ask us about 99. So just as you read the problem carefully, make sure you pay attention to what level of confidence the problem is asking you to use, and then choose the correct Z interval number from this table that's on the screen. So let's continue with practicing and learning this systematic process. So the French naturalist Count Buffon, in the years that Count Buffon lived, tossed a coin 4,040 times and got 2,048 to land heads up, and that is more than half. And we should know that if we flip a coin in the long run, the probability of it landing heads up should be 50% or 0.5. This time, Count Buffon got more than that. So construct a 95% confidence interval to determine if there is a reason to believe the coin was not a fair coin. So this process, calculate p hat, the proportion of heads up. Right? So Count Buffon had 2,048 heads up, and there were 4,040 times that he tossed a coin. That's the sample size. If we divide that, we get a probability of 0.5069. So we see it is slightly bigger than 0.5. The question we're going to be able to answer, is that too big? If that's too big, if that fits outside of our confidence interval, then I believe we have good reason to say that coin was not a fair coin. If that number fits within the confidence interval, then we have a good reason to say that coin is fair. It was just the chance of variation that this time he ended up getting more than half of them to turn heads up. So our rules of thumb that we want to continue to analyze and either prove or disprove. So our N, our sample size, is 4,040 times 0.5069. Is that truly greater than 10? Absolutely. The rule of thumb number 3, 1 minus p. So over here to the side, I'm going to calculate my 1 minus p value. 1 minus 0.5069. That's going to give us a pretty small number, 0.4931. 0.4931. So rule of thumb number 3 is 4040 times that 1 minus p number, 0.4931. Is that also greater than 10? And it is. So now we can estimate the standard deviation using that square root formula. So our square root, and this one the numbers are going to get a little weird looking just because those decimals are 4-digit decimals. So 0.5069 parentheses 0.4931. All of that divided by our sample size of 4040. So we have Desmos to help us crunch the numbers. Don't get freaked out and scared about the way those numbers look. Learn the process, learn this step-by-step approach, and be confident in using Desmos to help you with the numbers. So again, I'm going to do my square root, 0.5069. I was about to switch up those numbers. Parentheses, 0.4931. Close the parentheses, divided by, and then our sample size of 4040. And we get this standard deviation number, 0.0079. That is our standard deviation of the p hat. Now, again, I don't want you to get lost in the words and what does that mean so much. Learn this process. So 0.0079. That is the standard deviation. Step 4, construct a 95% confidence interval. So the math behind that is that 0.5069 plus or minus, not 2, but I'm going to use that value from the confidence interval chart. So when I go back to the previous slide, we are asked about 95% confidence. So I want to use that 1.96 factor instead of the full out 2. So plus or minus 1.96 times this standard deviation that came from that square root work. So if I carefully do that arithmetic, what I'm creating is an interval. I'm creating a lower limit and I'm creating an upper limit. And by doing this arithmetic, I should create the lower limit number to be 0.4914 and the upper limit number to be 0.5224. Right. So I'm not doing anything special for that. I'm just using Desmos to help me with that arithmetic. So when I go back to Desmos, 0.5069 minus 1.96 times 0.0079. Since I did minus, that's the lower limit number. So I have my mean, 0.5069, minus that z interval factor, 1.96, times the standard deviation. So there's the 0.4914. That is the lower limit number. And then I can simply go back and change that minus to a plus. And there's where the upper limit number comes from, 0.5224 rounded off. All right, so all of that math work now allows me to make a conclusion statement. So my conclusion statement that I'm going to type out instead of writing it so it's easier for you to read it. So my conclusion statement, I am 95% confident the true proportion of heads is between 0.4914, the lower limit, and 0.5224, the upper limit. Count Buffon's proportion does fit within that range. So we do not have the evidence to claim that that coin was unfair. So we're continuing to build off of and using prior knowledge, and we're adding to it this concept of confidence interval. Right. Next example might be a little bit more applicable to you guys. Recently, the ACT Incorporated reported that in a survey of 505 randomly selected college freshmen, that 363 returned for their sophomore year. Not everybody makes it to their sophomore year, and we have some numbers here to study and analyze. Estimate the annual return for all college freshmen with a 95% confidence interval. So it's giving us what confidence interval to use, 95%. So calculate p hat. Using this survey, our p hat, 363 over 505. And if we divide that out, we should get a p hat of about 0.7188. So again, that p hat is the sample proportion. The sample that we've surveyed, 0.7188, that's the proportion of the students who are returning their sophomore year. So we want to use that to make a prediction about the entire population, all college freshmen. That's what this 95% confidence interval allows us to do. So our rule of thumb, number one, our N was the 505 students. Our P, 0.7188. Is that truly greater than 10? Again, yes, it is. 1 minus P. And I need to apply that to 1 minus P. 1 minus 0.7188 is going to equal what? 0.2812. So our rule of thumb number 3 is 505 times 0.2812. Is that also greater than 10? And check it is. So just want you to create that habit of checking those two rule of thumbs. Most of the time it will, particularly with the problems that we're doing. Right. Now let's estimate that standard deviation of p hat. Now we're going to use that square root formula. 0.7188 parentheses 0.2812, and then all of that divided by our sample size of 505. I'm not just going to skip over the arithmetic for that, so let's look at that arithmetic. I'm going to use what you see in the first function box in Desmos, and I'm just going to change the numbers. That way I don't have to retype the whole square root. So the first number is 0.7188. The number inside parentheses, that's the 1 minus p, 0.2812. And then the sample size, instead of 4040, was 505. And by changing those numbers, I've now calculated that standard deviation, and I'm going to go just 0.02. I'm not going to write out those extra zeros. I'm not going to go all the way to the 6. So this standard deviation is about 0.02. That's what this square root formula is giving us. It's giving us the standard deviation of p hat. We're asked to construct a 95% confidence interval. So that 95% confidence interval is going to start with 0.7188. That is the proportion that we found from our sample, from our survey. And we're going to add and subtract. 95% confidence uses the factor 1.96 times that 0.02 standard deviation. And again, that's going to create this interval that we can say we're 95% confident with. So if I go to Desmos and carefully do that arithmetic, so I'm starting with 0.7188 minus 1.96 times, and you could do parentheses or the times button, times 0.02. Then we get the lower limit of 0.6796. 0.6796. And then if I simply change that to a plus, that's going to give us the upper limit number. So change that minus to a plus. Our upper limit number is 0.758. Now, at this point, all of our math, quote unquote, is finished. We need to take this information and make a conclusion statement. So our conclusion statement. I am 95% confident the true proportion of college freshmen returning for their sophomore year is between 0.6796 and 0.758. I'm just going to make that a little bit smaller, maybe, and a different color. Why not? But that's the type of conclusion statement that we want to be able to generate from our math. We are 95% confident that the true proportion of this topic we're asked about will be between that lower limit and upper limit number that we calculate. Two more examples that we'll practice through for this video. Again, I want you to see this process multiple times so you can develop this process and learn and understand step by step this systematic process. Right. So suppose a human genetics doctor is studying the eye color of newborn babies at UNC Rex Hospital. She used an SRS of 500 newborns and found that 62 of them had blue eyes. Estimate the proportion of blue-eyed newborns with 95% confidence. All right. I will try to go through this a little bit faster now. So our p-hat probability or p-hat proportion will be 62 newborns with blue eyes, 500 newborns in the sample size. 62 divided by 500 is 0.124. Rule of thumb number 2, 500 is the sample size times 0.124. Is that greater than 10? Yes. 500 times 1 minus p. 1 minus p, 1 minus 0.124. 1 minus 0.124 is 0.876. So 500 times 0.876. Is that continue to be greater than 10? Check. Yes, it is. Estimate the standard deviation of p-hat. Now we get to that big square root formula. Right, so our numerator is 0.124, parentheses 0.876, divided by our sample size of 500. And this time I am going to skip over the Desmos and trust for you to do that calculation on your own. We should get that p-hat, that standard deviation of p-hat, to be approximately 0.0068. Again, it's this systematic process. Step 1 first, p hat. Step 2, rule of thumbs. Step 3, this big square root formula. Step 4, now we do the 95% confidence interval. So we start off with the 0.124, which was our proportion, and we add and subtract 95% confident means 1.96 times 0.0068. That will give us our 95% confidence interval. And if we do that arithmetic carefully, we should get our lower limit to be 0.6267. Nope, that's not true. I'm looking at a wrong problem. I'm sorry. Nowhere close to that. We get our lower limit number to be 0.0952, and we get our upper limit number to be 0.1528. Now we have the evidence to be able to make our conclusion statement. So my conclusion statement, and I'm going to word it just a little bit different because you can see it worded a little bit different than what I've done on the previous two examples. So I'm going to type it out and word it this way. There is 95% confidence the true proportion of blue-eyed newborns is between, and then our lower limit number, 0.0952, and our upper limit number, 0.1528. I'll bold that. I'm going to make it a little bit smaller so it's not taking up quite so much space, and then turn it red. So there's our confidence statement. Now you could say I am 95% confident, or you can say like I have here, there is 95% confidence the true proportion of blue-eyed newborns is somewhere between this lower limit and this upper limit range. So I hope with these examples that each example you're getting a little bit better about learning this process and being able to apply this systematic process to work through these confidence intervals. The last example, example number 5. The North Carolina Department of Transportation, DOT, is researching the number of older, quote unquote, cars still in service. They've defined older cars as being more than 10 years old. They use an SRS of 5,000 car owners and found that 3,200 currently drive an older car. Estimate the proportion of older cars that are still in service with 95% confidence. So calculate P hat, 32 older cars, 5,000 for the sample size, and that gives us a proportion of 0.64. $5,000 times 0.64 greater than 10. Check. Yes, it is. 5,000 times 1 minus P greater than 10. So 1 minus P, 1 minus 0.64 equals 0.36. So 5,000 times 0.36 greater than 10. Check. Yes, it is. Estimate the standard deviation. Now we get to that square root formula. Our square root formula will be 0.64 in the numerator times 0.36 in the numerator divided by our sample size of 5,000. So that standard deviation with the square root formula .0068. Construct a 95% confidence interval using the value from the table. So our proportion was 0.64, plus or minus. 95% confidence means we use 1.96. Parentheses, this standard deviation, 0.0068. And that gives us our confidence interval of 0.6267 and 0.6533. Now we can make our conclusion statement about this 95% confidence interval. I'm going to start out, go ahead and make it smaller so that it's not quite so big as I type it out. Go ahead and make it red just because I can. I don't want to use a line color. All right. So there is 95% confidence. The true proportion of older cars still in service is between 0.6267 and 0.6533. There's our 95% confidence statement. For this video, I'm going to backtrack and revisit example number 4. Some of you may have calculated some different numbers because I think I made a mistake. I think I was looking at one of the wrong problem on my notes as I was writing this out for you. And I'm going to fix that now. It is step number 3. The setup I have is correct for step number 3, but the 0.0068 is not the correct number. There's the mistake where I copied down the wrong number from my notes where I've already worked it out. So for that problem, example number 4, that square root standard deviation, that should have been 0.0147. So 0.0147. So I apologize for that mistake the first time I worked it out. Again, I just copied down the wrong number from the wrong problem on my notes. Right. The next thing that is going to change is instead of that 0.0068, I will make that change to 0.0147. But fortunately, when I work out that 95% confidence interval, the lower limit and the upper limit numbers are correct. So I apologize for that mistake. I hope that does not create too much confusion. So this is the step-by-step systematic process that we want to learn, develop, and apply to help us make a 95% confidence statement about where the true proportion actually will fall.